that's just like thin German music.
I know at least the three are good.
Yeah, well, I mean, back then, I don't know about that.
Alrighty. So again, without knowing how long this is going to take, let me tell you about this. The next unit, the one I keep referring to, that's going to tie back to a lot of stuff, I think the title of that chapter is called Rotation. Okay? Because it turns out a lot of things in the world move not like left, right, up, down, but they rotate. A ton of things do that. So it's pretty important to know some of the basics about rotation. So it turns out a lot of the terminology that we use for that is very, very similar to what we use for, I guess, normal motion, which we're now going to have kind of another term to use to distinguish it from rotation. We're going to call it translation. So when we say something is translating, just picture it as like moving along a path somewhere, as opposed to rotating, which is kind of staying in place but spinning about some axis. Okay? So we actually saw some of this back in chapter 4. This is the first time I think we saw like spinning motion, and we probably more likely use the term spinning because I'm trying to think of all the different. We mostly just got into circular motion there. So one of the things I want to reinforce is that the terminology is the same, but the equations to describe the motion, while not identical, are analogous. I mean, they look almost identical with the exception of some Greek letters taking the place of more traditional, our alphabet letters. So let's try this. On number 1 there, this is kind of an old chapter 2, like first chapter of the year kind of a problem. Why don't you see if you can solve that using, and I copied some of the equations from the green page. I copied it onto the top of this page just to save yourself a little bit of hassle in digging those pages out. So why don't you see if you can take a little bit of time and figure out the answer to that, how far it will move question. Oh, and then there's some graphs to plot. Just rough sketches of the motion on those 3 graphs. Hello, Mr. McMahon.
Acceleration.
Yeah.
I love it. That was the like the fourth and short action. Yeah. Without power. I love this. Sorry, Jewel.
That's bad. Talking about giving away cash awards. I think it's square is like talking about cash awards or something like that. No, it was yeah, I love that.
All right.
It's so simple.
Part of the challenge here is knowing how much time you need. I'm gonna give some people more than enough time, some people not enough time. I'm just gonna. It's not like it's a race or anything. And this is a pretty general statement about solving any problem in here. A lot of times it's just taking inventory of what information you're given, to figure out what you need to solve for or whatever. So as you read through a problem like this, like putting labels on things, assigning them a symbol really helps. So if it says a car is moving at 16 meters per second when it starts to accelerate, what's that 16 meters per second become in that problem? Right, initial velocity, so I would just call it V naught. So I've got that number, 16. And it accelerates at 4 meters per second squared. That's a pretty easy one to identify. I should be careful about units here. How far will it move when it gets up to 30 meters per second? So that up to 30 meters per second becomes final. Now, in physics 1, we tend to write it this way. But you notice I just use the green page as my model, so they don't include the F. It's just regular old V. And all of these can have X on them, because they do on the green page. So in kinematics, if you were given 3 numbers, you could always find a 4th. And in this case, we were asked for how far it will move, which is, well, what's the symbol for that? It's delta x, or x minus x naught, depending on how you want to write it. The other thing would be time. There's a 5th quantity you could relate. We weren't asked for time, so I'm not going to bother with that. And so then finding the equation, which is, I didn't number them there, but these are actually 1, 2, and 3 off the green page. So which number are we using? Yeah, it is 3. X squared equals v naught x squared plus 2a, and I'm going to write delta x. And then without showing all the steps, plugging in the numbers that you have, doing proper algebra. Some of you will do all that great and then mess up an algebra step. You get to 80.5?
Yes.
Yep. All right. And then graphing this motion during the acceleration. The 3 traditional kinematics graphs, x, v, and a. Let me just draw it in the air. Just with your finger like you're drawing in the air. What would the shape of the position graph be? Getting faster. Oh, wait. Really shouldn't start like that. Start with some slope. It didn't start with 0 speed, so I really should start at like the vertex of a parabola. And the velocity graph. Right. Not starting at 0, starting at 16, and don't scale it, we're just sketching. And the acceleration graph. Now you got to be careful on this one. It's the one, well, really both of these, it matters where you put it. So a horizontal line, yes, but horizontal line where?
At 4.
Right, at 4, so above the time axis. Okay. It's a totally different kind of motion if either of these is down below the time axis. Not so much for this one it wouldn't matter, but these two it does. Okay, so there's, again, kind of a run-of-the-mill linear translation or kinematics problem. All right, so now, with a little twist, we start talking about things spinning. Okay, so like in a lot of factories, yeah. So you got things spinning like that because they're connected to things spinning like this. And then who knows what happens. I mean, this could be maybe connected to a belt, to another moving thing down here. You can have little rigs where a rotation of one thing causes linear motion of something else. That's always kind of neat. So what we refer to this as like the shaft, the drive shaft. If you're a car person at all, like your transmission turns the rotation of the, or the translation of the engine into rotation of the wheels, and that's done through what's called a drive shaft, something like that. Don't need to get into the too technical stuff. But what we do is we change the symbol. So instead of V's, we use the Greek letter omega. Instead of A's, and I don't like this one because the Greek letter alpha looks just like an A, but it's not A. It's a little more fish. A little fishy. Kind of looking. Yeah. And displacements, instead of X, we use the Greek letter theta. You just kind of make that little change. Your time doesn't change at all. So on number 2, I actually was just going to have you write the one equation that I didn't translate. I translated the first 2, but the third equation, equation 3 on the green page, just rewrite that in its rotational form over there on that one. And omega.
W.
Oh yeah, and don't call it W. I always do this. I put a little extra thing on it, and it's very kind of roundish. So just distinguish it from W. So that's an omega, and that's a W.
So it looks like W, just doesn't look. It's just
Yeah,
not
just
a
don't
W.
call it W. Most people call it W, and then I correct it and say that's an omega.
Theta naught looks weird.
What about like the actual omega sign? Is that a watch? Like what's that? That's not even probably your calculus.
I'm not sure.
You know, like the omega watches, how it's like a, looks like a roller coaster loop.
Well,
I don't know.
The
I
capital
don't,
omega looks
I don't think I've ever seen it. There's a capital omega that looks like this. Yeah. Yeah, that's capital omega. Okay, so what I want you to do now is read that next problem about the spinning shaft and do the exact same kind of kinematics with that you would do on a linear or translation problem, and it will work out marvelously. Oh, except that we've got to have units that are similar. So if I give you oh no, we can do that.
RPM.
RPM is revolutions per minute.
You change it.
I would say, because everything is given in revolutions per minute, you can just leave it in revolutions per
Should
minute.
we change the RPM per second to RPM per minute?
That,
Does that matter?
I don't think.
I don't know. It just looks funky.
That just means
Well, yeah, I know.
I don't know that that'll be necessary.
Okay. I just don't know.
I guess we'll find out. Just be a little careful with your units, and you'll find out if it's necessary or not.
I keep saying W in my head isn't the problem.
Oh yeah, those seconds are going to cause a problem.
Oh,
But you don't need to go to radians. So if you can just get your time units to match up, you'll be fine. You don't have to convert everything to radians. Because I asked you for revolutions, I didn't ask you for radians, we can avoid that extra step.
so so to change seconds, minutes, divide the seconds by 6.
So here's the whole RPM thing can cause problems. Let me suggest this: instead of RPM,
Do RPM.
just write it like that. That's really the more proper form. But then revolutions per minute per second, which is the acceleration number, would just be that. Just like having 2 time units in the denominator. And so think about railroad tracks. Those of you that had Mr. Jordan or most of the or HIP. So you're trying to change this to minutes. So there's your conversion factor. You get rid of seconds and get revolutions per minute squared, which would be the best one. So then you just got to know how many seconds makes a minute and how many minutes makes a second. I would say.
Multiply by 60.
Yeah, when you're involving denominators, I'm not sure I'd just try to think that out in your head. I would write it down. Even I would get confused on should I multiply or should I divide. If I don't write it down, it's a 50-50 shot of me getting that right. Little corner work is what I call that.
I'm gonna shut the door. That chicken smells so weird.
Yeah, it's not the best smell at 9 in the morning. Correct answer should come out in the 300s.
How does displacement work with the rotation? It just goes back to where it is. Shouldn't it be?
Yeah, so that's what's weird. With rotation, you actually accumulate. Every time you go
So
around once, you accumulate.
It doesn't just cancel out?
No, because otherwise you'd end up getting zero all the time. Every time it's back to where it started. And so that's why you kind of have to almost imagine a string wrapped around it, okay? And you're unrolling the string.
So isn't that more distance than displacement?
Technically, yeah.
Okay.
There is a problem when you call it displacement. The whole vector thing gets messed up with rotation.
Uh-huh.
But we don't worry about that.
Okay. I was just...
Yeah, what's different is you can't look at a snapshot of a rotating thing and tell what its displacement was, because it's going to just be back to where it was a little bit ago. Rotating things often have counters on them.
Yeah.
Like you've seen, well, like, you've probably seen a cross country where they
They
measure
have
out
the
of force.
measuring, yeah, the 1 meter circle.
It's called a trundle wheel. Yep. So if you're not getting something in the 300s,
I did.
315 to be exact.
Oh, yes.
Have me take a peek at it. We're not. 360. You messing with me?
No, I would say.
Are you lying?
Because it's exactly.
I got 316.
Did you do some?
What?
There's oh, 1.66. What did she do?
What did you do?
What's the point? You go to rating. Oh, you went to. I converted this into rows per minute. If you converted these others into it's all across R's.
Yeah.
Oh, yeah.
Did you subtract the both
Yeah,
of those?
yeah.
Or divide? Okay, because that's what I did.
You have it.
What did you wrong?
Yeah, I think.
Give it on the side.
We kept the other three there. That
You
was
can go in during that.
So with the time,
Set on
is that
your
like
finger now.
in minutes or?
Did you ask about
when
it?
you round it,
Mine's only like one.
Oh, I didn't know that.
it's all right. Really.
She basically just said, so I'm during one time in minutes or seconds.
You can go during lunch and during that period. I'm in the study period one.
Well,
Okay.
that was gonna take hours or however.
So,
It works out.
we'll carry on with this when you come back. And I'll try to find some old AP questions that relate to this. The more we practice those AP questions, I think the more confident you'll feel. Oh boy.
You know, I feel like I understand this better now than I did back when we actually did it. So, you know, this is better.
You know what that is? That's time. That's your
I
brain.
didn't know what I was doing back then, so that was the biggest problem.
Yeah, that's how that works.
Virtual physics is so difficult.
Haven't you ever done that? Well, like you go back to something you haven't seen since middle school and you've never looked at it again and you're like, it's just crystal clear?
Yeah.
That's your brain making all of these connections. You don't even know it's happening because it happens while you sleep.
Yeah, no, it is much easier than it was back when we first did it. I'd absolutely